Well, thank you everyone for joining us this afternoon for our session on advanced hypothesis testing for impact and discovery. We're delighted to have Dr. Gaskins here with us. He's an associate professor in the Department of Bioinformatics and Biostatistics that's going to be speaking with us today. So Dr. Gaskins, welcome, and you can feel free to get started.
All right. So let me just start a little bit by just giving a little bit about my background. So I am, like Christy said, associate professor in the Department of Bioinformatics and Biostatistics at the School of Public Health. And I've been here at U of L since 2013. And so my main methodological research areas involve developing statistical methods to handle longitudinal data, missing data, mixed outcome data, as well as sort of focusing on new Bayesian methodologies. But while I've been here for the last, 12 years or so, I've also been highly involved in collaborative work with different groups in the School of Medicine and across campus. And that work's primarily been with OBGYN, radiation oncology, and surgery, as well as different other groups. And sort of the reason that I am here is sort of as a member of the Research Design, Compliance, and Data Management Core of the LCTRC. And so just a little bit about the RDCD core. If you're not familiar, our role or our goal as a part of the Clinical Translational Research Center is to provide state-of-the-art statistical support to help provide guidance on the use of electronic health records, and then provide guidance, resources, and training for other researchers who are using the core. So obviously, we're sort of here in the goal of achieving the last aim here with providing training. And so the Research Design, Compliance, and Data Management Core Director is Mai-Ying Kong. She'll be giving a talk next week on some other aspects related to statistics and data management. But just to give a plug for if you are interested in reaching out for support in your work from the RDCD core, you can go to the LCTRC, there's so many acronyms, the web page, and find the RDCD core page, and there will be a button here to request support, and that'll have a brief form for you to fill out, and then that will go to Dr. Kong, and she can help get you in touch with someone that can help facilitate consultation on your particular research project. So, okay, our little sort of plug about the core out of the way, we'll get into sort of what we're here to talk about, which is hypothesis testing. And so before we get into hypothesis testing, I want to take a step back, because hypothesis testing is really one aspect of what we call inferential statistics. And so when we talk about inference, we talk about making conclusions about some population based off of what we see in our sampled data, within the data that we either observe from our clinic, that we've gotten from some experiment in a more structured lab setting, or wherever we are obtaining our data from. So the first thing that we want to think about when we're trying to perform statistical inference is that we need our data to be randomly sampled from the population. And in most cases, we don't actually have that. Typically, what we settle for is that our sample is representative of the population. And we won't really today get into the issues associated with that potential mismatch, but that is an important piece. But what I do want to sort of focus on is when we're talking about performing inference, one of the things that we want to think about is sort of imagining the parameter that describes some feature of our data. And so this is some mathematical value that is always going to be unknown. And we'll sort of clarify in a little bit sort of what this may look like in particular examples. But the parameter is basically the thing that we want to perform our hypothesis on. And so I'm going to use my sample data to get some estimate of this population parameter, and that's going to be descriptive statistics from our sample. So in a lot of cases, the parameter may be the mean, the population mean, or the difference between population means, and then my estimate is just whatever I get from the data. And again, in a lot of these cases, and the cases that we're interested in today, we want to perform some kind of hypothesis test about our population parameter related to some specific scientific hypothesis. And so this hypothesis, I need to be able to write down mathematically in terms of whatever that population parameter is. And so we'll see that in a little bit. But before we get into that, I sort of want to distinguish what we're not going to be talking about or thinking about today, and that is prediction. And so, prediction is another sort of goal that we often have when we're performing statistics or when we've got a particular data. There are a lot of sophisticated and effective methods for prediction, a lot of sort of novel and new statistical techniques, a lot of machine learning techniques. Obviously, over the last couple of years, we've got a lot of new AI techniques that can get us at prediction. All of these, or at least most of these, are going to operate sort of functionally as a black box, right? We don't necessarily know what is happening inside these algorithms. We feed in data, they give us a prediction. And so for that sense, they aren't well suited for hypothesis testing, where I have a particular claim that I want to be able to evaluate, and I need to sort of specify a particular mathematical model that is going to define that. And so, we're not really talking AI methods. We're not going to be talking terribly machine learning methods. There are, for the most part, these aren't the best strategies for hypothesis testing. They're good strategies for prediction goals, but not really for hypothesis testing. So we're going to be mainly focused on sort of classical statistical theory sort of framework for hypothesis testing. So with that said, what is the hypothesis testing framework? And so probably most everybody knows this. This is sort of what we learn in Stat 101. But again, I think it's really imperative to sort of remind ourselves of the terminology and the framework as we get into more specifics. And so the first test to performing a statistical test is we have to actually specify what the hypotheses that we're interested in. And so that comes in sort of two components. I need a null hypothesis, H0 or H0, and that's going to represent the default belief that we want to disprove. So typically this means there's no treatment effect, there's no association between the exposure and the outcome, something, again, often involving the word no, right? No difference, it's our null belief, our default belief, the null hypothesis. And then the thing that we want to claim, that we want to be able to quote unquote prove, is usually going to be what we call the alternative hypothesis. And that is going to be denoted by H1 or HA and represents the conclusion that we want to make. So we'll sort of illustrate this through an example that we did was really at this point a while back with some OBGYN collaborators. And so after patients have a C-section, they're usually prescribed pain medication, and often those include opioids. And so they were interested in sort of a new counseling framework to see whether that was going to decrease opioid use post C-section. And so, we need to define a primary outcome for this study, and that was going to, in this case, be the number of pills taken during the first 10 days post-discharge. So they called the patients 10 days later, and while they were on the phone, counted up how many pills remained, and we were able to determine, how many pills that means they had taken. And this was set up in a randomized trial setting. So half of the patients received the standard drug counseling, and then the other half received some new counseling that they had developed. So again, if I want to first specify my hypotheses, what I need to think about is what are the parameters that I'm interested in. And so there's sort of three parameters here that we can talk about. The first is what we'll call mu0, mu0, the mean number of pills taken by patients in our standard counseling. And so we don't know the value of mu0. This is an unknown parameter. It represents the entire population. I can use the data from, however many patients receive the standard counseling, get the sample average, and use that as an estimate for mu0. But I don't know, I don't know, and I never know the sort of quote unquote true value of mu0. Similarly, I have a population parameter mu1 that represents the mean number of pills taken by patients who receive our new counseling. Again, I don't know the value of mu1, but if I was able to, see what happens if I gave every possible woman post C-section this new counseling and counted up how many pills they use, that's what I would require to estimate or to learn mu1. And then the parameter that we're probably actually interested in we'll call delta, which is just the difference of these two, right? The difference between mu0 and mu1. And this is, for this example, our treatment effect, right? And we can interpret this within this context as the number of additional pills taken by patients in the standard counseling group relative to the new treatment. And so I'm going to typically think about delta here as the parameter that I'm really interested in. And so my null hypothesis, right, needs to represent my default belief, the thing I want to disprove. And what I want to disprove is that the treatments are the same, right? And so my null hypothesis is that the number of pills taken under the standard counseling, mu0, is the same as the average number of pills taken by the new counseling. And so that's equivalent to this population parameter delta being equal to 0, right? And then my alternative is going to be that the number of pills taken under standard counseling is different from the number of pills taken under my alternative. And so my alternative here is going to be delta not equal to 0. So one thing to keep in mind, right, is that every hypothesis test that we ever encounter corresponds to some set of parameters and some particular H0 and H1. And so anytime I run a statistical test or anytime I get a p-value, these things are in the background somewhere, right? There is some set of parameters that I am making a test for relative to a null and alternative hypothesis. And so, anytime I have a test or a p-value in my paper, do I know what that parameter and hypotheses actually is corresponding to? I think it's sort of a good thing for us to be asking ourselves as we're working and doing various research and writing up our results. So, I think the most helpful analogy for thinking about a statistical test is jury duty. For those of us that have done jury duty, right, it's not always a lot of fun, which I think for many people also feels like a statistical test, right? May not be much fun. But again, I think it's a good analogy here. So, when during the course of a trial, right, the jury has to decide whether the defendant is guilty of some particular crime, right? And the way it's supposed to work, right? If you've watched enough Law and Order, right, we know the jury is supposed to presume that the defendant is not guilty unless there is overwhelming evidence to the contrary, right? And that sort of overwhelming evidence we call beyond a shadow of a doubt. Right. And so the null hypothesis, right, the jury's default belief, right, is supposed to be that the defendant is innocent, right? So that's our null hypothesis, right? The default belief is that the defendant is innocent. And then the alternative, right, the thing that the prosecution is trying to get us to conclude, right, is we want to get enough evidence to conclude that the defendant is guilty. So that's the alternative. That's sort of, we're accumulating evidence to try to change our mind, right, from innocence to guilty. And so we obtain the evidence. That's sort of the analog of our data collection. We run the statistical test, which is the analog of the trial. And then we reach the conclusion either by rejecting the null hypothesis and therefore concluding the alternative, right? We reject the null. The evidence that we saw during the trial tells us it's not possible that this person was innocent. They must be guilty. Or if there's not overwhelming evidence, what is the jury supposed to do? They're supposed to fail to reject, right? They're supposed to stick with their default belief. And they don't actually claim, right, that the defendant was innocent. What they claim is the defendant was not guilty. Right. And that's sort of the important distinction with a statistical test. And that's what's really important when we think about, again, with the statistical test, is that if we don't conclude the alternative, we did not prove the null hypothesis, we did not prove that the defendant is innocent, we only conclude that they're not guilty or there wasn't enough evidence, we typically call this fail to reject. And so again, we can only really make an affirmative decision in terms of the alternative of guilt. We don't make a decision in favor of the null. We may just stick with our default belief. So, having sort of reminded ourselves of sort of the decision framework, we'll go back to this example, right? So we ran this trial. We had 134 patients that we I guess we're I think able to get the complete data. We are able to get them on the phone 10 days later and count up the pills and whatnot. And so this is what our data looks like. So under the standard counseling, we had 68 patients. They took an average of 20.87, roughly 21 pills per person. And the standard deviation from individual to individual was 8.9. Under our new counseling, we ended up with 66 patients with data. With an average of 19.89 pills, a standard deviation of 10. So, what do we see in this experiment? We saw a small decrease, basically 0.98 pills fewer. Patients in the new counseling group used 0.98 pills fewer on average than the standard. And so we should ask ourselves, right, okay, so we saw a treatment effect, right, 0.98 pills. Is this likely to be due to differences in the treatment, or could this one pill drop be explained by the random variability in pill use across our 134 patients, right? And that's, sort of mathematically the question our hypothesis test is trying to ask, right? Is trying to distinguish between whether our result, whether the effect that we've observed here, a 0.98 pill drop, whether that's likely due to differences in the treatment or whether that's likely to be, or whether that can be explained by random variability. And so again, sort of to push another analogy, imagine I flip a coin 20 times and I get 14 heads and 6 tails. And so my question is, okay, I got 14 heads, only 6 tails. That feels like I got a whole lot more heads than tails, right? But is this actual result, 14 heads, consistent with the randomness of a fair coin? That would be our null, our H naught, our null hypothesis, right? That I have a fair coin, there's nothing fishy going on. Or would getting 14 heads versus out of 20 flips imply that I'm using some sort of trick or biased coin? That would be my H1, right? And so that is sort of the framework or the sort of like the framework that the mathematics of the hypothesis tests are sort of looking at, right? Is this result that I got, a 0.98 pill drop, is that consistent with randomness I would observe under the null hypothesis? Or does that imply something else is going on? And so that's without trying to get into the mathematics, that's fundamentally under the hood sort of what the hypothesis test is trying to do. And so for this example, right, with the cesarean opioid use, right, we've got 2 groups. We've got a continuous outcome. So, the test that I would want to use is my 2-sample t-test. And so if I plug my data into software, R or SAS or whatever, whatever web page I determine, I can find to give me a 2-sample t-test, I end up, it's going to return a p-value at me, right? It's going to say, okay, your result is a p-value of 0.555. Okay, but what does that mean, right? What does my p-value mean? How do I use that to make a decision? And so, what is a p-value? A p-value is some decimal number between 0 and 1. And the way we turn that into a decision, right, is if my p-value is less than alpha, whatever alpha I pick, then I'm going to reject the null hypothesis and conclude that the alternative hypothesis is correct. So if my p is less than alpha, I've got quote unquote a lot of evidence against my null hypothesis. We've run the trial. The defendant looks very, very guilty. It's not possible that they're innocent. We're going to convict, right? That's what we're concluding. We conclude the alternative that they are guilty must be correct. If our p-value is bigger than alpha, then we fail to reject and we conclude that it is possible that H naught is correct. Now, again, we should want to distinguish. I am not proving H naught. I'm not even saying H naught is likely. I'm really just saying H naught is plausible, right? It may still be the case that the defendant is innocent, right? There is at least a shadow of a doubt that H naught is a plausible explanation for the data that we have. Now, of course, here I'm comparing my p-value to alpha. I've got to pick a value of alpha. We almost always pick alpha to be 0.05. We could potentially also argue whether that's a good choice or not. But typically that's the value we pick and we sort of don't argue about it. And so here in our opioid case, right, the value p bigger than alpha means that we fail to reject H naught, right? So this 0.98 pill drop would be consistent with the sampling variability that we would have in opioid use. It is plausible that our treatment is not providing any any meaningful benefit, right? That we have not changed the average number of pills that the patients are taking. And again, we sort of said this earlier, right? Anytime I have a hypothesis test, I have a pair of hypotheses and a parameter. Equivalently, anytime I have a p-value, right, there is some hypothesis test, some H naught and H1, and some set of parameters. And so again, I would sort of challenge us, like as we're writing down or, writing papers and things, every time I put a p-value in my manuscript, do I actually know what hypothesis test I have run to get that p-value? And is that a meaningful hypothesis test? Are the hypotheses that correspond to that p-value actually meaningful and things that I want to actually be testing? So again, every p-value corresponds to some hypothesis test, some set of hypotheses, and some parameters. Okay, and back to our sort of jury duty analogy, right? Again, in reality, there are one of two options. Our defendant either is truly innocent or our defendant is either truly guilty. And we on the jury, right, never actually know this, right? We never know. We get, we see however much evidence during the course of the trial, and we may feel fairly confident in our assessment, or we may not, but we never really know whether they're innocent or guilty. But of course, if the defendant is actually innocent, if the null hypothesis is true, I may have made one of two decisions. I may have either the jury may have decided to acquit. They failed to reject the null hypothesis. They looked at the evidence and they said, we still have at least a shadow of the doubt that they may not have committed the crime. We're going to acquit. And obviously, in this case, that's a correct decision. It could be the case that the jury convicts this truly innocent defendant. And in that case, that would be sort of in statistical parlance, what we call a type 1 error. And so the statistical tests are designed such that the probability of a type 1 error is alpha. So that the alpha that we were comparing our p-values to, that is the probability that we make a type 1 error, right? That's the probability that we send an innocent person off to jail, right? We send or we promote a incorrect, a false, a null hypothesis, a true null hypothesis. Alternatively, if the defendant is actually guilty, and we obtain enough evidence that our p-value is less than alpha, we reject the null hypothesis, we conclude the alternative, we convict this guilty defendant. That, of course, is the correct decision. The incorrect decision would be, of course, acquitting the guilty defendant or failing to reject a true alternative hypothesis. So when there actually is a treatment effect and we fail to detect it, that would be a type 2 error. And that we denote by probability beta. Generally speaking, we can make a guess at beta in the design. If we're doing a sample size calculation, we need to make a guess or a choice about the type 2 error that we want in our experimental design. But generally speaking, we don't actually have control over the type 2 error, right? We've got control over the type 1 error because that's based off of alpha or 5%, but we don't, in the case of running our experiments, generally have control over the type 2 error, again, except at the design stage. So, we should also talk about what a p-value is not, right? And so the p-value formally gives the probability of seeing data more extreme than the data we actually observed if there is no treatment effect, right? And so, in the case of this analogy, what is the probability that an innocent defendant would look even more guilty than the defendant we actually observed on trial? And the most important thing, or maybe the most important thing to say about what a p-value is not, is it is not the probability of the null hypothesis, right? We do not describe probabilities of our hypotheses, right? Either it's a case that the treatment, is effective or not. We just don't know. And so the p-value isn't a probability of, the treatment being effective or of any of our hypotheses. So, what I encourage folks to think about the p-value is not to worry about sort of the probability definition of a p-value. The easiest way is just really to think about the p-value as a level of agreement between our observed data and some null hypothesis. And so, if I have a very small value, that indicates my data is inconsistent with my null hypothesis. I have very, very low level of agreement between the data I actually saw and my null hypothesis model. And so, again, if I have very little agreement with the null hypothesis, then I want to reject the null hypothesis and conclude the alternative. My larger values of my p-value, say p bigger than 0.05 or p bigger than alpha, tells me that I could see this type of data if my null hypothesis is true. So I should not change my belief away from the null, right? And again, that means we're going to fail to reject the null. The null remains a plausible explanation of the data we observed. And so we can get into sort of the mathematics of how these p-values are calculated a little bit. Again, more just to show that it's maybe not the probability that you think it is or that is most useful to us, rather than to encourage you to think about p-values sort of in this context, right? So again, it's the probability of seeing data more extreme than the data we actually observed if our null was true, in this case, if there was no treatment effect, right? And so here, the observed treatment effect that we saw in this cesarean opioid example, right, was we saw an estimated difference in our sample means, or in our means, of 0.98, right? And so what do I mean by more extreme than the data we actually observed? So I want to know what's the probability that if I reran this experiment such that I was using a treatment that I knew had no difference from my standard counseling, what's the probability that just by random chance I would have ended up with a group difference of 0.98 pills or more, or a negative 0.98 or less. And so that's sort of what this bell curve is representing. All the areas that are shaded, the probability bigger than 0.98 on my right side, the probability less than -0.98 on my left side. And if I add that shaded area up, I end up with 55%, which is the p-value that we started with, right? The p equals 0.055. And so again, all of this is really the main point that I'm trying to drive is that the p-value is typically not the probability that we thought we were calculating. And so I would, again, generally encourage most users not to try to figure out what probability a p-value corresponds to, just to sort of, again, think about it as a level of agreement between my observed data and the null hypothesis. And sort of on those lines, so this is sort of old, but I think folks still maybe don't know about it, and I think it's still really good advice and a good framework. So back in 2016, the ASA, the American Statistical Association, so the main professional group for statisticians, released this statement on statistical significance and p-values, and they proposed sort of 6 fundamental principles that really all scientists should be thinking about and should use when they are encountering and utilizing p-values and sort of our standard hypothesis testing framework. And so, again, I think these are important, so I want to sort of bring them to the group today. Firstly, is that p-values indicate how incompatible the data are with a specified statistical model. So again, like I said, we should think about the p-value more as the level of agreement between our data and the null hypothesis, that the null hypothesis sort of being the specified statistical model is talking about. Again, our p-values don't measure the probability that the studied hypothesis is true or the probability that the data were produced by random chance alone. Number 3, it would, the ASA would encourage that scientific conclusions and business policy decisions should not be based on whether a p-value passes a specific threshold. I think the addendum that they didn't specify is, manuscript acceptances shouldn't be based solely on whether the p-value passes a specific threshold as well. Number 4, proper inference requires full reporting and transparency. That's not actually a p-value statement. That's a p-hacking statement, which I probably won't talk more about today, but again, sort of an important thing to keep in mind. P-value doesn't measure the size of an effect or the importance of a result, and by itself, the p-value doesn't provide a good measure of the evidence regarding a model or hypothesis. Again, the p-value measures sort of the evidence against our null hypothesis, but it isn't really measuring the evidence in favor of the alternative, the thing that we claim. And so again, that is, I think, a sort of important piece that often gets lost when we're dealing with p-values. So what should we be using instead, or what should we be using in addition to our p-values to help sort of mitigate some of these concerns? So the first thing to say is that statistical significance is different from practical significance, right? And so whether a result is practically significant depends a lot on how large the estimated treatment effect is, and also how precise my estimate of that treatment effect is. And so confidence intervals are really a good tool to help with this, and are really sort of the best tool, and are arguably more informative than running the hypothesis test. And so, I would encourage us to basically always include the confidence interval with our hypothesis test, at least as much as we can. And so, what do I mean by a confidence interval, right? It's the interval of numbers that represent the set of most likely values of our unknown population parameter, right? So again, I've got a population parameter that I don't know the value of. My hypothesis test is testing whether that population parameter takes some particular value. Again, in our case, testing the null, whether delta is equal to 0. And so they're based off of our data. I have some set of best values for delta. And so again, confidence intervals are going to give me evidence on the size and clinical relevance of my result. The width of my confidence interval is going to provide some idea of the precision. And then even when my result is not statistically significant, utilizing my point estimate and the confidence interval may point to my result as being important or worth further study, even if my p-value is above that alpha 0.05 threshold. So, in our opioid example, what does this look like? So my estimated treatment effect here was 0.98 pills. And my 95% confidence interval is negative 0.28, negative 2.28 up through positive 4.23, right? And so, this means, right, our data would be consistent with any treatment effect ranging from our new counseling session is associated with patients taking 2.28 more pills on average, up through our new counseling leads to 4.23 fewer pills on average. And so again, I can think about my confidence interval as providing the set of parameter values for my delta that are consistent with my observed data. Clearly, I can see that the null hypothesis value of delta equals 0 is one of the values in my confidence interval, right? And so how should I be thinking about that? Well, again, my confidence interval represents basically the plausible set of values for my population parameter. Delta equals 0 is in my interval, right? So treatment effect of 0 is one of the many plausible values for my true treatment effect delta. And so again, that's consistent with not having evidence to reject delta equals 0, right? And so my confidence interval basically always gives me the conclusion from a hypothesis test while also giving me more information about the actual effect size and precision. So again, it's a better marker to use in general or to supplement sort of what we're using from the hypothesis test. Another option is to report our estimated effect sizes. This is a strategy that's very popular, like in psychology and some of the social sciences. You don't necessarily see it a ton in sort of the health and medical literature, but I think it's often a good strategy to use as well. And so here, basically, you can calculate an effect size measure that's basically the same sort of calculation you would have done in your power calculation. So if you ran, a sample size calculation, you had to posit a value for the effect size, the sort of minimum effect size that you would have the power to detect. Well, after I've observed the data, I can actually calculate, sort of based off of the data, what was the effect size that I observed, right? And that may help me. And so in this case, it's basically going to be my treatment effect divided by the subject level variability. And so again, we've got a difference of 0.98 pills as our treatment effect. And we think about that relative to the standard deviation between individuals, which is 8.88, at least in the control group, right? And so this tells us, that treatment is associated with a 0.11 standard deviation change in our outcome. Again, that's not terribly high. An effect size of 0.1 would not, again, be quite strong in this case. But in other cases, again, this can be a helpful measure, especially if I want to try to argue that my result is practically significant, even if it's not statistically significant. So a couple other things that we should be thinking about as we are running our statistical tests, as we're thinking about the tests that we need to run. And I'm looking at the clock. I'm going to run out of time. I expected that I was going to run out of time, so that's okay. the different things that we need to think about as we're sort of considering what type of test and how we're going to do that. So first is that the type of test that we're going to use depends on the predictor or predictors that I'm using and the outcome. And so, you can find sort of a table or list like this anywhere, but certainly, depending on what outcome I have, whether it's binary or unordered categorical, whether it's ordinal, whether it's, an approximately normal continuous, whether it's a continuous that's not normal, or a survival outcome, right? I've got different choices of what the appropriate test is, based off of my outcome, as well as sort of each combination of what, if I have a single predictor, if it's binary, I use one test. If it's categorical, I use one test. If it's continuous, I use one test. Or if I have multiple predictors, I can use different choices as well. But maybe, one big question that I need to think about, and one question that is going to have sort of a big impact on sort of the power of my tests and the interpretation of my tests and sort of the validity of our analysis is sort of what I'm using in terms of predictor, or whether I've got a single predictor or multiple predictors, and how we're dealing with that. And so should start sort of with simpler cases, right? Tests with a single predictor. And so generally, and not always, but often this is sort of the test that we claim we're going to run, right, for our primary outcome or our main hypothesis, right? Often we've got sort of one main exposure and one main outcome, and we're going to run that test as our sort of primary, again, our primary analysis, right? And of course, if I'm only using a single exposure or a single predictor, then we typically call these unadjusted tests or marginal tests, right? I'm not adjusting for any of the other potential confounders or the other predictor variables that I might have access to. Of course, this is going to look at the association between our primary exposure X and our primary outcome Y, and ignore the impact of any other confounder or predictor variable. And so that, of course, is the potential problem with running an unadjusted test. Now, if I'm in a randomized trial where I'm randomly assigning my exposure or treatment group to individuals, then I know that I'm going to have approximately the same distribution of our confounders U within each group. And so in that case, there isn't actually really any need to control for our confounders or for the other predictors in our analysis. And so, in a randomized trial, right, the marginal test or the unadjusted test is going to work just fine. And it's often going to be our preferable test to consider. But if I'm in like an observational study where I can only really claim that X is associated with Y, there I'm really going to need to worry about whether there are some factors or some factor or other predictors within this sort of U set that's going to impact both my predictor or both my exposure X and my outcome Y. And so, what are my tests with multiple predictors? Well, in practice, right, often this is a follow-up to our unadjusted test. Even if I expect that my, that I have confounders that are going to play a big role, it in many cases will still run the unadjusted test just to see what's going on as sort of a crude relationship between X and Y. But I will often then follow that up by running these adjusted or multivariate tests where I'm going to control for my other confounders or my other predictor variables. And so, pretty much regardless of what outcome type I have, all of these tests more or less end up with sort of a regression structure. So they usually look something like Y equals alpha, which is sort of our unknown intercept, plus beta times our primary exposure, and then plus different terms, gamma 1 times our confounder 1, plus gamma 2 times confounder 2, and so on, plus some error, right? And of course, if I have a binary outcome, then this is, like a logistic regression instead of a linear regression. If my Y is a survival outcome, this is a Cox regression instead of a linear regression, right? But they all sort of have the same sort of regression structure. And so here, right, what is the test that I'm interested in? I'm interested in testing beta, right? Beta is my coefficient of the X, which is the primary exposure, right? So that is, right, the hypothesis test that I am considering myself to be interested in running here, right? Is there a role, is there a relationship or an association between my primary exposure X and my outcome Y? And so I'm going to use this regression type structure to assess that. And I'm going to use my various confounders U1, U2, and so on to adjust or control for their impact both on my exposure and on the outcome. And so as a sort of silly example, we might be interested in what's the role of kale on BMI, right? So do patients who eat a lot of kale have lower BMI, right? Kale's supposed to be healthy, et cetera, right? And so I can certainly do a marginal analysis. I could fit like a Pearson or a Spearman correlation between the amount of kale an individual consumes and their BMI. And that will, of course, give me an unadjusted effect. I could also instead fit this as a sort of simple linear regression model. So for every unit increase in kale consumption, beta is going to represent that slope, how much that unit increase in kale impacts BMI, right? So my null hypothesis is that there is no association between kale and BMI. That's the same as my regression coefficient being equal to 0 versus my alternative that beta is not equal to 0. But certainly, I can imagine there are going to be a lot of relevant factors that, in terms of who is eating a lot of kale, that may also be associated with BMI, right? Certainly, probably folks that are more health conscious are eating more kale, and they're also the same people who have lower BMI in general, right? And so it's easy to imagine that this is not going to be a good representation of the actual role kale plays in controlling weight, right? And so maybe I need a model with some different confounders, right? So maybe I want to assess the effect of kale while also controlling for level of exercise, for age, and for sex, right? Maybe those are confounders I have in my data set. And so I could fit this model, and now I would be assessing the effect of beta, right, while controlling for my other factors. And so this changes our interpretation of beta. Right now, beta means, right, for two individuals who have the same level of exercise, age, and sex, what is the difference in BMI if the second individual has 1 unit higher kale consumption, right? And so, again, where you want to think about it as what's the effect of kale while controlling for the other confounders for someone with the same exercise, age, and sex. So if I fit this model, the first thing I should expect is that the magnitude of my estimate, the magnitude of my effect is going to be attenuated. It's going to drop, right? The impact of kale is going to look a lot smaller in this model when I'm adjusting for exercise, age, and sex. But what is the impact going to be on the power of my statistical test for beta? So, sort of two things are happening at once. One is I'm explaining away some of the variability in BMI by using my other variables, right? I would certainly expect exercise is going to be a really important predictor for BMI. And so that's going to explain away a lot of the variability. Age and sex are also going to play a big and important role. So that's going to, on the one hand, increase my precision in the effect of beta, leading to higher power. Sort of on the other hand, if I'm including more predictors in this model, that is sort of going to counteract that, and that can actually negatively impact my precision. And so I have to be really careful about adding the predictors that are going to help me, but not adding too many predictors, or else I'm then lowering my power. And so one of the ways that we can think about which predictors I want to include in my model, the first thing is the best strategy is always to use our scientific knowledge rather than letting sort of the data decide which predictors to use. Generally, using our scientific knowledge, knowing or sort of based off of the literature, what are the features that are likely to impact both kale consumption and BMI, and using that to determine what predictors to include in our data. Now, what I can do if I have a hard time making that claim, making sort of that choice, is it is still common, right, to look at sort of the marginal relationships between our exposure and each of these predictor variables, between our outcome variable and each of these predictors, right? One of those two is usually already going to be in our table 1. And the other one may also already be a table in our set of results. But then what I want to do is, based off of those relationships, either as estimated from the data or sort of intuitively my scientific knowledge, the predictors that I want to include in my model are what we call the true confounders, predictors that have an association both with the exposure and with the outcome. Again, those are critical to including in our model. If a variable is associated with the outcome but not associated with the exposure, that is still often useful to include in our model. Those are variables that will help explain away variability to increase our precision. And so that's useful. If I have a variable that's associated with the exposure but not the outcome, generally speaking, I don't want to include it in my model. That is likely to decrease my precision and lower my power, is if I'm including those types of variables. And what I may also need to do is then further refine or reduce my set of confounders, because I don't want collinearity. And what we mean by that is I don't want predictors that are capturing the same information. Another thing to say here, as an alternative to fitting these regression models, a common strategy or a useful strategy is to use sort of the causal inference framework and to use propensity scores. And the way these work is that if I have a 2-treatment group setting, I'm basically going to estimate a propensity score model, which gives me a probability that patients receive the treatment based off of each of our predictors. And then I'm going to use some sort of reweighting or matching approach so that I have a revised cohort such that the group of patients that are untreated or in my control group are similar to the group of patients in my treatment group on these sets of confounders. And that way I've got balance in my other predictors, and so I can actually just use a marginal test. Because we have adjusted for the effects of these different predictors through our propensity score weighting rather than through a regression model. Okay, so let me just hit one or two more things, and then we'll just sort of abandon the last couple slides. But one important thing is to think about whether I want to run a one-sided or two-sided hypothesis. And so in the cesarean example, right, I said that I was interested in knowing whether my new treatment decreased the amount of pills that our patients take. But yet, the alternative that I actually said we were going to use was delta not equal to 0, right? And so how do I know whether to use a one-sided or a two-sided hypothesis? So my one-sided hypothesis means that I'm going to pre-specify the direction of my effect. And critically, I can only claim statistical significance if the data ends up pointing in that same direction. And so, again, in my opioid case, the claim that I could have made was that the alternative was going to be delta bigger than 0, means I'm only testing if my new counseling leads to fewer pills being taken. And of course, the nice thing here is that matches our intuition. It may be a little closer to the scientific hypothesis that I'm interested in. And it's going to allow us to make a claim that the treatment effect only if the number of pills actually decrease. So generally, though, we're going to go for the two-sided hypothesis, and that's going to investigate any relationship between the exposure and the outcome. Whether, again, our new counseling session leads patients to take fewer pills, like we're hoping, or, if it turns out that this new counseling session is, or this new counseling is associated with worse outcomes, I would still want to know that, right? And so typically we want to use the two-sided alternative. It's going to allow us to detect a difference in either direction. There is a slight power loss. So if I use a one-sided test, I typically have slightly higher power. Of course, my two-sided hypothesis test is robust to hypothesis misspecification. And I would say that basically it's preferred in almost all circumstances. Again, I would very, very rarely encourage folks to use one-sided hypotheses. And many tests that we run, basically any test that involves more than two groups at a time, is going to be inherently two-sided. And the choice to use a one-sided test and which direction I'm interested in can only be made at the experimental design stage. Once I've started collecting data, I better not make a choice about the one-sided test at that point. Okay, so let me, I think we'll skip the clustered data stuff. I think we'll also skip parametric and non-parametric. I think we'll share these slides, but, and then I was going to say a little bit about equivalency trials. And then let me get to the other slide, which was things that I already knew I wasn't going to get to that are also important, right? And so, again, we also haven't actually talked at all about experimental design issues. And our choice of hypothesis test is highly related to how we're going to design our experiment. Certainly if we're in a more design-based setting versus an post hoc observational study. We haven't gotten into multiple comparison issues, which have a big impact on power and making those choices. And then we talked a fair amount about regression from, multivariate regression from the perspective of hypothesis testing. But that's different, right, from prediction. It's also different from sort of more general modeling, where I want to understand of the variables that I have, what's associated with BMI, right? Instead, we were interested in what's the effect of kale on BMI while controlling from other things. I can imagine a setting where I just want to know sort of what's associated with BMI. Okay, so let me stop there. Again, use the form on the LCTRC web page if you want to set up a consultation. You can also reach out to me, and then I will get to these questions that Mystery posted. Okay. I'm not sure whether you all can see the questions or not, so I'll read them. Why are p-values good at preventing us from fooling ourselves by chance, but bad at telling us how strong the evidence is? And is that an inherent contradiction of the interpretation of p-values? So I mean, what I would say is that p-values are doing exactly what they're designed to do. It is that we often don't know what they're we often misinterpret what they're trying to do, right? And so again, to go back to here, right? If I flip my coin, I get 14 heads and 6 tails. This corresponds to a p-value of basically 0.1, right? And so this tells me I don't have enough evidence that my coin is not fair. Now, at the same time, I have flipped this coin and I've gotten a 70% success rate, right? And so All my p-value is basically accounting for is the variability that we would expect to under the null hypothesis, right? And so, like, I think to your point, that is exactly the sense in which it's good at preventing us from fooling ourselves by chance, right? It's going to say it is possible, it is, not unreasonable to expect to get 14 heads when I flip my coin 20 times. But it doesn't really tell us, you know, what there's no part of that calculation that's actually accounting for a model for the alternative, right? How likely, my coin is to be unfair, or, if I had a 70% fair coin, what would happen there? And so, again, I think I would say it's a limitation to how we interpret and what we're asking p-values to do. Right. And so, again, I think I would say, like, these are sort of supposed to be our guides as to what we want to get out of a p-value. And then the second question, why can a p-value be meaningful in a retrospective study that was never designed to detect anything in particular? It seems p-values are more meaningful in prospectively powered studies. So I think that is, yeah, I would say, like, that's a really good point. I mean, certainly any prospectively powered study is almost certainly inherently superior to a retrospective study in a variety of ways, not specifically related to p-values, right? I mean, like, clearly the most important thing is that I actually have control over, my exposure assignment, and I dramatically simplify the way in which I have to worry about the role and the impact of confounders. So, I think in a retrospective study, there is an sort of, I guess I would say, like, an inherent weirdness into what the probability meaning of sort of the p-values work, in that, again, like, I am not prospectively collecting the data. I mean, starting today, if I think about a retrospective study that I might perform, if the data is already there, like, the result is already fixed. And so there is a sense in which, like, maybe from a probability perspective, sort of the probability is not there. But I think, like, also that's maybe not so much a p-value issue, because, again, ultimately, to the extent that I want to think about p-value as a probability, the p-value is, again, like, not a probability with respect to the data that I am using, right? The randomness in the p-value is for if I repeated the study under a null hypothesis framework, right? And so that, I guess, I don't know that it's a p-value issue. I mean, again, I guess you can question sort of how meaningful any statistical analysis or any sort of retrospective study is. But that I would argue maybe that's more of a design question than a, like, strictly p-value question or a hypothesis test question. As well as getting into, I mean, I think from a practical standpoint, the other aspect to that is that in a retrospective study, we often see the p-value course after some p-hacking and some data dredging and finding the most meaningful effect. And so I think there's also probably a sense in which the p-value and the results that we are seeing in the literature are biased in a way that, again, is sort of a mix of bad science, either in terms of deliberately looking for hypotheses that are supported by our data, as well as, like, publication bias and some other things related to that. I don't know if that really answered those questions at all, but those are sort of the things that at least come to mind as potentially relevant to that discussion. I know we're over, but if other folks have questions, either want to post in the chat or unmute and share, can maybe try to give a more straightforward answer than I just did.
I think with the settings I have, they may need to raise their hand and then I can unmute them. I'm not completely sure. But if there is a question you would like to speak, raise your hand and I'll make sure that you can unmute.
Oh, I think Mai-Ying has her hand up.
I will add some comments. Jeremy, thank you. It's a very wonderful talk. And then for second one, for perspective study, we do use this observational study to do these perspectives, the retrospective studies. In that case, we kind of, the new hypothesis seems the p-value is test whether the coefficient is 0 or not. So for that case, we new hypothesis corresponding the coefficient is 0, alternative is not 0. We still use that a lot in practice. I just want to add a little bit on this. And then if the model, we are, even for observational study, if we are able to adjust all these confoundings, is still valid. P-value is still valid. Yeah, that's what I'm thinking. But Jeremy, you can chip in if you think otherwise. Kind of.
Okay,
Thank you,
so
Dr.
then I
Khan.
guess
It looks like, yeah.
Yep. Go ahead, Christy, sorry.
Oh, no worries. Yeah, it looks like there are no more questions. So thank you everyone for attending this afternoon. And like Dr. Gaskin said, if you have any follow-up questions, you can feel free to email him. And I will be sending a follow-up email and I'll have a link to the consultation form if you would like to request support with your project. So thank you very much, Dr. Gaskins. We appreciate you joining us this afternoon. It was a very informative session.
All right, thank you. Bye.
Yeah, thanks everyone. Bye.